And sometimes it gets a little hectic out there. But right now, we gonna up you on how we just chill.
Dollar 7 digits, call up Bridget, her man's a midget. Plus she got fringe, yo, I can dig it. Here's a 40 swig you know it's...
In this video, we'll go over magnetic fields, such as how are they produced and how do they look like in three dimensions. The most familiar example for everyone is probably a bar magnet, like shown here. It has a north pole and a south pole. So there's something going on in this piece of material that it's been polarized into two different types of magnetic areas, north and south pole. And then there are electric field lines leaving from the north pole and finding their way to the south pole. And here on the blue we see the magnetic field lines. The magnetic field it has a magnitude and direction, so it's a vector quantity, capital B. The units of B, or electromagnetic field, are Teslas, or for short, just T. So we can produce magnetic fields by permanent magnets, like in this case, or the more common way in practice is to use electric current. So as shown in this figure, electric current running on a wire or a conductor produces a magnetic field also. So here we see these magnetic fields that circumfere the conductor. They are strongest at the closest to the wire, and they get weaker as we go further away. So here we have these field lines as well. In fact, it's still unknown what exactly is going on inside a permanent magnet when it produces field like this, but it is believed that it has to do with electric currents inside this material, or movement of electric charge in general. And just that you know, the suspect of causing all of these is the spin of an electron. So some kind of movement of electron that produces magnetic fields, and they manifest themselves in a macroscopic scale, like this in a bar magnet, for example. But let's come back to the example for magnetic fields in a conductor. With the bar magnet, it's a simple rule. The magnetic field lines go from north to south, but for a conductor like this, there are no poles, north or south poles. So which way are the electric or magnetic fields in this field then? When dealing with magnetic fields, you will end up using something called the right-hand rule in all its variations in most problems. So what the right-hand rule says, so if you grab this conductor in such a way that the thumb of your right hand points to the direction of the current, then the way your fingers are curled will indicate the direction of the magnetic field. Like shown here, the current goes up and the magnetic field would be counterclockwise in this case. Here we have an example where the conductor is a continuous ring that has current running around it. So if you would take your thumb and point it to the direction of the current, you will notice that your other fingers would curl in such a way that the magnetic field points to the right, and that is indeed the case. Something else one can see here as well. The same thing applies here as with electric fields. So the strength of a magnetic field can be represented in these figures by how dense these lines are, so how close they are to each other. So we have a strong field here in the middle of the ring, and then as we go outside it gets weaker, and also gets weaker as you go further away. We can observe the same here with the case of the straight conductor. The lines are more dense next to the conductor, so there's a strong field there, and also we have a strong field here near the poles of the bar magnet. So, and that makes sense based on our observations of magnets. The field is stronger the closer you are. As you are well aware, also Earth has its magnetic field. At this point in time, it originates from the geographic south and curls around the planet to the space and ends up somewhere in the northern hemisphere. The magnetic field in Earth hence has north and south pole, like it would be a giant bar magnet there. But in fact, the magnetic field is believed to be due to the charges flowing in the liquid core of Earth. So whenever there are charges flowing, that means there's current inside the planet in this case, and that will form these magnetic field lines. And if we place a magnetic needle, like in compass, it will experience a torque in the magnetic field in such a way that it tries to align itself with the magnetic field lines. So hence the magnetic or compass indicates us the direction or the axis between north and south poles, or the north and south magnetic poles. As you can see, the actual north and south poles of Earth, they are a little bit off from the direction of the magnetic dipole, which is at some angle, as you can see. Here are a couple of quick exercises. So first one, does the Earth's magnetic field have greater magnitude near the poles or near the equator? And the hint says, look at the field lines. As we discussed, the density of the field lines is an indicator of the strength of the field. So we definitely have more field lines at the poles, at the magnetic poles, than at the equator. So the field strength is larger near the poles. So near the poles. And then in exercise B, a straight wire carries current directly toward you. And in what direction are the magnetic field lines surrounding the wire? So there's a conductor pointing straight towards us from the screen. So that is, in that case, the direction of the current is signified by this kind of symbol. So this would be outward from the screen, and if we would have a current going into the screen, it would be noted by this kind of symbol. So we have current coming towards us, so that means we have to point our right hand thumb towards us, and that curls our fingers in the counterclockwise direction. So our field lines would be like this. So there's current I here, and the field lines are then running counterclockwise.
Kids get broke for their skins when I'm in close range. I throw game.